In this video, we discuss learning outcome number 4 from lesson 6.3, which is all about the sampling distribution of sample variance and its relation to the population variance. So just as a reminder, the sampling distribution of sample variance is the distribution of all values of that sample variance as squared when all possible samples of the same size n are taken from the same population. The notation that we use is S squared for sample variance. And this is an estimator of the population variance, which is denoted by sigma squared. Since the mean of the distribution of sample variances is always equal to the population variance, we say that the sample variance is an unbiased estimator of that population variance. A couple of things you should note about sample variances. When you look at the distribution of sample variances, it tends to be skewed to the right. So it has a long right tail, as we'll see in the next slide. And as I just said, the mean of the sample variances is equal to the population variance. So that means that sample variance is an unbiased estimator. In other words, the expected value of the sample variance is equal to the population variance. So the sample variance is a good estimator of that population variance because this is what we would expect to get. In symbols, we can say this basically. The mean of the sample variances, notice that that's a subscript, is equal to the population variance. So here's a graphic that just illustrates that exact same idea. So let's say we've got a population of size capital N, and we randomly select n values with replacement from that population. And then with each of those selections, we find the variances for each sample. So we do that once and we find a variance. We do that again and we find a variance. And we do that again and we find a variance. And we do this all of the possible ways that we could randomly select n values from that population. So we do this and we get every possible sample variance. And then we look at the distribution of those sample variances. It turns out that when you look at that distribution, you'll see that the sample variances tend to have a distribution that looks like this. It's skewed to the right, has a long right tail. But if you find the mean of those sample variances by taking each sample variance and multiplying by the probability that you get that particular sample variance and then adding them together, it turns out that the mean of the sample variances is actually equal to the population variance. So sample variances are unbiased estimators. So here's an example. It's that same population that we've been working with in the last two videos. Here we've got a population, it only has 3 elements in it, 4, 17, and 11. And our first goal will be to find the population variance. And then we're going to practice creating a sampling distribution by finding all possible samples of the size n equals 2, selected with replacement, and then finding the sample variance for each sample. And then once we've done that, we can summarize that sampling distribution of sample variances in the form of a probability distribution table. And then once we have that, we can use that probability distribution table to find the mean of the sample variance and show that it's equal to the population variance. So first, let's find the population variance. Well, in order to find the population variance, we need the mean, because remember, variance is a measure of variation from the mean. So first we compute the mean just by adding all of the values in our population together and then dividing by that population size, n equals 3, get 32 over 3. And then it turns out that the population variance is calculated this way. You take each x value, so that's the 4, the 17, and the 11, and you subtract the mean, which is that 32 over 3. You square those and you add them together, and then you divide by 3. And it turns out that when you do that, you get 254 over 9 as the population variance for those 3 values. Now we're going to come up with all possible samples of size n equals 2, selecting with replacement, and then find the sample variance for each sample. It says sample mean. I meant to change that. Okay. Finding the sample variance for each sample. Now, These are the samples. There are actually 9 possible samples of size n equals 2 when you start with 3 values in your population, because you're sampling with replacement. So when you have 3 values, 4, 17, and 11 in your population, and you're choosing the first one for that sample of size n equals 2. The first number in your sample could be a 4, a 17, or 11. So you select the 4, the 17, or the 11, and then you put that back, and then you select again, either a 4, a 17, or an 11. So that results in these 9 samples. We had 3 options for our first selection and 3 options for our second selection. So according to that multiplication counting rule that we talked about in chapter 4, we've got 3 times 3 possible samples, or 9 samples. So we can either choose 4 first and then choose a 4, a 17, or an 11, or we can choose 17 first and then choose a 4, a 17, or an 11. And then we could choose 11 first and then choose a 4, a 17, or an 11. Now, in order to calculate the sample standard deviation, we need sample means. So you're going to take these 2 numbers, you're going to add together, and since the sample size is now 2, you're going to divide by 2. So we'll have 4 plus 4 divided by 2 is 4. 4 plus 17 divided by 2 turns out to be 10.5. 4 plus 11 divided by 2 is 17.5, and so on, and you calculate all of those means. If you want to, you could do this in Excel, and that would be fine. You might have a column for that first choice, the 4, the 17, and the 11, another column for the 4, 17, 11, 4, 17, 11, 4, 17, 11 that would go with each of those first values. And then you would have Excel add the 2 elements together and divide by 2 to get these sample means. Okay, so once you have the sample means, you can calculate sample variances this way. Now, lowercase n, remember, is the sample size. In our case, the sample size is n equals 2. So n minus 1 in the denominator just ends up being a 1. Now, I know I said that pretty fast. I'm going to write all of this down on my piece of paper, and then I'll share my paper with you, and we'll go through how we would calculate the sample variance for each of these samples. Okay, so we've got our samples over here and our means here. Now remember what this means. You're going to take each of the values in your sample and you'll subtract the mean, then you'll square those, you'll add those together, and then you'll divide by n minus 1. But each of these has 2 elements in it. So these have sample size n equals 2. So if n equals 2 for each sample, then n minus 1 is going to be 2 minus 1, or just 1. So we really don't even have to divide by anything. All we want to do is take each x value on our list, subtract the mean, square those, and then add them together. So basically what I'm doing here is I'm taking the 4s from our sample, and then I'm subtracting the mean in each case. Then I square those and add them together, and then I would typically divide by n minus 1, but that's just dividing by 1. Now notice that this sample just has 2 4s in it, and so we get 0 squared plus 0 squared, so the sample variance is just 0. Well, that's exactly what we would expect, right? Because the variance is a measure of that variation or that deviation from the mean. If you have a sample and all of the values are exactly the same, there is no variation. So it would make perfect sense that since there is no deviation from the mean, since there is no variation in that sample, that this measure of the variation would be 0. So the same is going to be true down here with the 17s. You're going to have 17 minus 17 squared plus 17 minus 17 squared. And these 17s in red come from right here, the sample mean, and so you just get 0. And then when both values are 11, you're going to have a 0 there as well. Okay, now for these other guys, we're not going to get 0 because there is some deviation from the mean for each of these guys. So we'll have 4 and 17 here. We're going to subtract the means. We'll square those and add them together. Here we'll have 4 and an 11. We're going to subtract the means and add those together. And then we've got 17 and 4 again. Whatever we get over here for this 4 and 17 will be the same answer for the 17 and 4. So let's fill in our means. Okay, so I get 4 minus 10.5 squared plus 17 minus 10.5 squared. And I get 169 over 2, which is about 84.5. Now that was using a 4 and a 17, which had this mean. So when I use 17 and 4, I'm still going to get an 84.5. Okay. Now for this one, I've got 4 minus 7.5, and I'm squaring that. Then I'm adding 11 minus 7.5, and I'm squaring that. Then I get 49 over 2, or 24.5. That was when we had a 4 and 11. We have a 4 and 11 here with the same mean, of course, because it doesn't matter which one's first, we're going to get the same mean. So the sample variance here is going to be the same as the sample variance there. So that's going to be a 24.5 as well. Okay, so now we've got this 17 and 11. So those are our values. We're going to take each of those and we're going to subtract the mean, which is 14. So I've got a deviation of 3 here. 3 squared is 9. A deviation of -3 here. -3 squared is 9. 9 plus 9 is 18. So that's with the 17 and the 11. We've got another 17 and 11 here. So we're going to have an 18 as our sample variance there as well. And the 11 and 17, we actually already calculated. Oh wait, that's what I just did right here. So that's it, is it? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, those are our values. So we've got our sample standard, or not sample standard deviation, our sample variations now. Now let's go back to our slides. And let me see, do I have the same values here? 0, 84.5, 24.5, 84.50, 18, 24.5, 18, and 0. Okay, great. Same values that I got when I prepared the slides. Now we want to take this and summarize it in the form of a probability distribution table. So we've got all of these different sample standard deviations, but we see we've got a little bit of repetition. This 0 appears 3 times. The 84.5 appears twice. The 24.5 appears twice. The 18 appears twice. So we can summarize all of that in the form of a probability distribution. I'll do this on my paper here, and then we'll look at the slides and see that we get exactly the same answer. So the possibilities for our variance are going to be listed here in our probability distribution. Now we tend to write these in ascending order. So you want the smallest sample variance first. So 0 is there. And the probability of getting a 0, well, there were 3 different ways that we got a 0 out of 9 different samples. So 3 out of 9 is that probability, or 1/3, same thing. Then the next one up, let's see. I did the zeros. The next one up appears to be 18. We've got an 18 here and an 18 there. So there were 2 out of 9 ways that we got an 18. The next one is the 24.5 and the 24.5. So that goes there. 2 out of 9 ways that we get a 24.5 as our sample variance. And then the highest variance that we had was this 84.5, and it appeared twice. So we have a 2 out of 9 chance of getting a sample variance of 84.5 if we are selecting samples of size n equals 2 from this population of size capital N equals 3 that consists of values 4, 17, and 11. Okay, so that's our probability distribution for the sample variance. Let's go back to our slides. Yep, I got the same values on the slides. That's a good sign. And now lastly, we want to show that the mean of the sample variances is equal to the population variance. Now remember how we do this. Back in chapter 5, when we discussed discrete probability distributions, we said if we have a number of possibilities for the value of some discrete random variable x, and we know the probability associated with each of those values, so that this is a true probability distribution. And remember, it's a true probability distribution if this is a discrete random variable, and the sum of these probabilities is equal to 1. We also have true probability distributions that have continuous random variables, but they wouldn't be listed in a table like this. But we've got a discrete random variable here. And in this case, instead of just an x value, it's the population or the sample variance, s squared. And then we've got the probability of getting each of those sample variances as 1/3, 2/9, 2/9, and 2/9. Notice that if you add those together, you get 6/9 plus 3/9 is 9/9. So this is a true probability distribution. Now, if I want the mean of this random variable, this discrete random variable, all I do is I take the values of that variable and I multiply by the corresponding probability. So that's going to give me a 0. That's going to give me a 4. This is going to give me a 49/9. And this last one, what is that? 84.5 times 2. 169/9. Okay, so you multiply those guys together and then you add them together. And that is the definition of the mean of that discrete random variable, s squared, which happens to be the sample variance. Now, if I add those together, this is what we get. We have 4 plus 49/9 plus 169/9. And we get 254/9. Let's go back to our slides. Remember that population variance that we calculated at the very beginning? It was also 254/9. So we see that the population variance is equal to the sample variances, or the mean of the sample variances, excuse me. So that sample variance is a good estimator of that population variance. We call it an unbiased estimator because the mean of the sample variances is the population variance. And again, remember that's exactly what we want. The sample variance is supposed to estimate the population variance. And if we are able to calculate its mean, that's the expected value of that sample variance. It's a good thing if it gives us the corresponding population parameter, in this case, the population variance. So that is one concrete example that shows you a sampling distribution for sample variance. Now, in this example, we're thinking about that process of rolling a die 5 times and then finding the variance of the results. Now, the way Mr. Triola does it is different from the way that we just worked out that last example. I'm going to share my paper with you again so that we can discuss this and so that I can show you some calculations. Okay, so for rolling a die 5 times, we have 6 possible outcomes for the first roll. And then we've got 6 possible outcomes for the next roll. 1, 2, 3, 4, 5, or 6. And the same is true for the next one, and the same is true for the next one and the next one. So if I want to know what are the possible outcomes that you could get when you roll a die 5 times, it's going to be 6 times 6 times 6 times 6 times 6 times 6. It's going to be 6 to the 5th, which turns out to be 7,776 possible outcomes. Now, if I were to try to list those 7,776 outcomes, I would be here for a really long time, but I could find the probability associated with each of those outcomes. So for example, it's possible that we roll a die 5 times and we get a 1 5 times in a row. We get a 1, a 1, a 1, and a 1. There's only one way to do that, to get all ones. So the probability of rolling a 1, a 1, a 1, a 1, and a 1 is one way out of those 7,776 ways. Now, also associated with rolling a 1, a 1, a 1, a 1, and a 1 is a sample variance. Now, the mean of this is clearly just the sum of all those ones divided by the 5 ones that you have. Since they're all identical, the mean is equal to 1. So the sample variance here, which is computed using this formula, the sum of the x's minus the means squared divided by the sample size minus 1. Well, in this case, it's just going to be 1 minus 1 squared plus 1 minus 1 squared plus 1 minus 1 squared, all the way down. You've got 5 ones, 1, 2, 3, 4, 5. And then you take that and you divide by the sample size minus 1. Looks like the sample size, we can think of that as 5. So the sample size minus 1 is 4. And so we would get a sample variance of 0, because all of those are going to be 0 there. So we have a 0 as a sample variance this time, and we want the probability of getting a sample variance of 0. It turns out to not be 1 over 7,776. That's the probability of rolling a 1 4 times. But the probability of getting a sample variance of 0 is actually 6 out of 7,776. Now, if you're wondering why that's true, well, it's because there are 6 different ways you can get a sample variance of 0. You can get a sample variance of 0 if all of these are 1s. You can get a sample variance of 0 if all of these are 2s, if all of these are 3s, if all of these are 4s, all 5s, or all 6s. So there are 6 ways that the mean would be equal to that value that keeps repeating itself 5 times. And then we'd see a bunch of expressions like this. So if these were all 2s, the mean would be 2. We'd have 2 minus 2 squared plus 2 minus 2 squared all the way across. We'd add those together and we get 0. So there are 6 ways out of 7,776 possible outcomes that we could get a variance of 0. And then there are other possibilities as well. Maybe we have 4 1s and a 2. Maybe the first 4 are 1s, or the first 3 are 1s and the last one is a 1. Now, all of these are going to have the same mean, and then because they have the same mean and they have the same number of 1s and the same number of 2s, they're all going to have the same sample variance. So in this case, I believe the mean would be the sum of those guys, which is going to be 6 divided by 5. So the mean would be 1.2. If I take each of those and I subtract 1.2, and I square those and add them together, and then I divide by 4, that's going to give me the sample variance for all of these guys. Now there's only one way, well, actually, pretty sure that there's only one way to get that sample variance, and it's if you're in one of these categories. So we'd have a 5 in 7,776 chance of getting the sample standard deviation or sample variance of 1 minus 1.2, and you're going to have that 4 times, plus 2 minus 1.2 squared, all divided by 4. So let's see what that is. I'm just curious. 1 minus 1.2 squared plus 2 minus 1.2 squared divided by 4 equals 0.17 as our sample variance. So there is a 5 in 7,776 chance that you'll have a sample variance of 1.17. The only way it's going to be 1.17 is if we're here. I believe that's true. I'm wondering if there are other combinations of values between 1 and 6 that would give you the same sample variance. Anyway, we could do this for all of the possible outcomes here. For all 7,776 outcomes, we could compute a sample variance. Then we can look at how many times that sample variance appears out of that 7,776 possible outcomes. So does it appear 5 times? Does the sample variance appear 6 times, like the sample variance of 0? And we can find the associated probabilities. And we would have to do this. We'd have to do this a lot until the sum of these was equal to 1, so that every possible sample variance is covered. Then we would take these guys and multiply them together and then add to get the mean of the sample variances. Okay, so that is not what Mr. Triola did in this example. He said instead of looking at those 7,776 possible outcomes and then thinking about the probability of getting each of the possible sample variances, what he did instead was he rolled a die, or had somebody roll a die 5,000 times, or maybe he simulated rolling a die 5,000 times, and then found the sample, or 10,000 times, excuse me, and then he found the sample variance in each case. The question is, well, what do we know about the behavior of all the sample variances that are generated if we keep doing this indefinitely? Now, this is coming from repeating the process 10,000 times. He says the true sample distribution would involve repeating this process indefinitely. I don't think it's necessary to repeat it indefinitely. I think we would just have to be aware of the 7,776 possibilities and the variances for each of those possibilities, and then the number of times those variances showed up out of those 7,776, so that we could get the true probability of each sample variance, just like we did in the last example. But notice what he has here. He says maybe the first time you do that, you have a sample variance of 1.8. Maybe the second time you do that, you get a sample variance of 2.3. Third time, you get a sample variance of 2.2, and so on. Well, it turns out that if you do that 10,000 times and then you compute the mean of those sample variances, you get a mean of the sample variances of approximately 2.9. Now, he says that that's the same as the population variance of 2.9. In order to confirm that the population variance is 2.9, I'd like to work this out on my sheet of paper. So I'll share my paper with you again. Actually, I've got enough space on this one. So let's say that this is our sample space, or we can roll a 1, a 2, a 3, a 4, a 5, or a 6. If I want the population variance, we take each of those x values and we subtract the population mean, we square it, and then we divide by the sample size. And that's going to be equal to 6 in this case. So in order to do that, I need to compute the mean of these guys, and the mean comes from adding all of those numbers together and then dividing by 6. I believe we did this in a different video. I believe the answer is 3.5. Yep, we got a 3.5 there. So what we're going to do is we're going to take each of these guys and subtract 3.5 and then square those answers and add them together. So I'm actually not going to write out a column like that, but that's the idea. We're going to say, let's take our 1 and subtract 3.5 and square it, and take 2 and subtract 3.5 and square it, and 3, subtract 3.5 and square it, and so on, until you've taken every outcome over here and you subtracted the mean. And you've squared them, and you divide by that size of the population, which in this case is going to be 6. So we say 1, we open parentheses, 1 minus 3.5 squared plus 2 minus 3.5 squared. Oh, whoops, delete, delete. You need to close the parentheses first, then square it. 3 minus 3.5, close parentheses squared, plus 4 minus 3.5, close parentheses squared. You just keep going. And then you take that answer and you divide by 6. And we get 35 over 12, which is approximately that 2.9 that they were talking about. I prefer that exact answer of 35 over 12, but we could use the decimal approximation 2.9, or we could use the exact repeating decimal 2.916 repeating. Okay, so now let's go back to our slides. So this says, because the values of 1, 2, 3, 4, 5, and 6 are equally likely, the population variance is calculated using that formula that I just used. You take 1, 2, 3, 4, 5, and 6, you subtract the mean, which is 3.5, and you divide by 6. Now, that means our population variance is that 35 over 12, or approximately 2.9. And because the sample variances are unbiased estimators. Sorry, I lost that word for a second. They're unbiased estimators of the population variance. If we take the mean of all of those sample variances that we calculated from those 10,000 samples, it turns out that the mean is approximately 2.9. Now this is just showing you that distribution again. Notice it's a frequency distribution, and he's got different probabilities, or excuse me, different sample variances down here. You could have a sample variance of 0, and there's a sample variance that's above 7.5. But so all of that is shown here, and then we have the frequency out of those 10,000. That is the number that had that particular sample variance. Now, if you wanted to compute the mean of these sample variances, and you're thinking of this as being 10,000 tries of an indefinite number of tries so that the true sample size is infinite, then what you would need to do in order to compute the probabilities that you need in your probability distribution for this is to use that relative frequency approximation of probability. So you're going to take the frequency that you have, and you'll divide by that 10,000. That's going to give you a relative frequency. So that's the proportion of the sample variances that you have that were given by that particular value of the sample variance. And you'd multiply the sample variance with that proportion together. It's just like multiplying by the probability. And then you would add, and it turns out when you do that, you get approximately 2.9. So the sample variances have a mean of that is exactly equal to the population variance, which happens to be 35 over 12, or approximately 2.9. Now in this slide, I wanted to show you that the sample variances are supposed to be skewed to the right. Notice that they are skewed to the right. So it's not that characteristic bell shape that we see for a normal distribution. It looks similar to a normal distribution, but it's skewed. It has that long right tail. So that is the end of our discussion of the sampling distribution for sample variance. Note that sample variance is an unbiased estimator of population variance. But if we look at the distribution itself, it's a little skewed to the right.